Thank you for the invitation and thank you for the introduction. I think you already had a chance to look at my title. My co-authors are Seshadri Commander and Temi Kolda, both are from Sandia National Labs. All right, so I'll be talking about a graph model, but to start with, why do we need a model at the first place? Well, the idea is, first, we cannot always share data, and that's because that may for several reasons. It may for security. Well, it may be for privacy reasons. Well, you don't want to make you don't want your data, personal data, to be made public. Or, well, sometimes the data is too valuable. I mean, for instance, for financial reasons, the data may be too valuable to share. But at the same time, people do realize, well, they need algorithms, they need good algorithms, and they want these good algorithms to work well on their data. So there's a lot of motivation for sharing information. So I want to tell you everything you need to know to design good algorithms, but nothing more. And a good compromise here is to release surrogate data. So that will be, well, essentially to have all the nice properties of my own data, but at the same time, I'm not sharing to tell the real data. It will be a randomized data, and if any coincidence, any match to the reality will be just coincidence. So that's the idea. And, well, you also need models for testing your algorithms. For instance, if you're a graph algorithms designer, Kamesh was talking about it, for instance, well, you want to know the scalability of your method. And to test the scalability, you need the same problem at different sizes. And then you can say, well, here's my algorithm, and it speeds up linearly, then, well, good. So it works well. So another reason is that, well, you want to tweak the parameters, and you want to make sure that your algorithm works for slightly different instances. So there's in some of the areas where there are only a few data sets available, over-tuning to these a few data sets is a big problem. People find an artifact in that particular data set and tune all their algorithms for that, and the real data sets, the algorithms do not work as well. And another problem is characterizing, well, in some areas, well, there's plenty of data, and then the problem is, we read a lot of papers, we tested our algorithm on these 100 data sets, and ours is the best. And you look at this other paper, we tested our algorithm on 100 data sets, ours is the best. So if you know these data sets, these 100 data problems on this one and the other one, you can tell what algorithms work well when. But if you don't, and that's often the case, if you're not a domain expert, then, well, you're in trouble. You cannot tell which algorithm you should be using. But if you can parameterize the search space and say, my algorithm will work best if your problem, alpha parameter for your problem is less than 0.5. And then you measure that parameter in your data set. If it's less than 0.1, well, I'll use your algorithm. And also, these models can provide insights into, well, for instance, what kind of communities you should expect in your graph. All right, so we do need models. I hope I was able to convince you that we do need models, but what do we want in a model? For graphs, the first thing is, well, you need heavy-tailed degree distributions. I'll not restrict myself to power law degree distributions, well, because these distributions come in all shapes and forms. But at the same time, they're heavy-tailed. So we have a skewed degree distribution, and there's a heavy tail. Well, that picture is from the Barbasi paper in 1999, famous, where it claimed that, well, the graphs have power law degree distributions. The other common theme is, well, community structure. There were a lot of talks, well, just the preceding talk, for instance. Well, there is good local, there are communities in these graphs. So we should be able to generate, well, if we have a good model, we should be able to generate these degree distribution and these communities. Well, how we measure that is a problem that I'll come back. And we want to be able to fit the real data. That's, if I'm claiming that my model generates graphs just like real ones, and you come up with a real graph, I should be able to generate something like that graph. So I should be able to measure whatever I want to measure in your graph and generate instances just like that one. And for our purposes, well, we want scalability. So, well, you may have heard about Graph 500. Well, they generate giant benchmark. The goal is to promote HPC research on data-intensive computing, and it's a benchmark designed for that. And for we want to generate graphs that with, well, 2 to 40 nodes. And we're in the initial lab, so that's large problems is our special interest. All right, so let's start with the first one. So how do you preserve the degree distribution or generate something with a given degree distribution? So there are a lot of models out there. They come with very nice stories. You want to listen to the story, but at the same time, they cannot even regenerate a given distribution. One exception is this chunk-Lu model, which I believe is underappreciated. So it's also known as, well, there's similar models, but Chung and Lu came up with the model. Newman described the same thing, essentially the same as the edge configuration model, and it's also often referred to as weighted Erdos Renyi model. It's a very simple model. I think its simplicity is working against it. People want more fancy models. And the idea is very simple. Well, I know, tell me the degree distribution, assign a probability for each edge, and that probability will be proportional to the product of the two vertices. If the probability of a edge between vertex I and vertex j is di times dj, and you normalize it by the total number of edges, or sum of the degrees. It's as simple. And if you do that, if you implement this, you can regenerate the degree distribution. There you see these red and blue dots. They're just overlapping because Chung-Lu can regenerate a given degree distribution. And if you want to implement a scalable way, instead of going ahead and flipping a coin for each potential edge, you repeatedly insert edges, and that's you only insert m edges, and essentially you'll generate a graph. All right, so degree distribution is not a big problem. How about the second one? Well, community structure. The problem with community structure, before we even start, it's not a well-defined problem. There are a lot of algorithms for that. And just think about the talks you've heard in this workshop. There are a lot of algorithms for that. And the problem is that, well, you can run two different algorithms on the same graph, and you'll get two different, totally different community structures. And even the sizes will not match. And there's no way in telling this one is better than the other. So we're not there yet. And even, well, let's fix it, stay on, choose one algorithm. Well, in two different implementations of the same algorithm, you can find different communities in the same graph. Even more than that, if you have, well, if you can run the same algorithm on the same data twice, and for different runs, you can see different communities. So it's not a good, finding these communities is not a good metric. When I say metric, we should all be able to measure the same thing, implement the same thing, and without any ambiguity, we should be measured exactly the same thing. And it should be easy to measure. So instead of these community structures, we're using clustering coefficients. And clustering coefficients I'll define in a minute. It's the same thing. We can all compute the same thing. And if anyone comes up with a different number, well, whoever that person should go back and check the code. So there's a bug. So that's the idea. All right, so the clustering coefficients. And this is what we'll use as an approximation to the communities. And you can define it in different ways. You can define it per vertex. The idea is it's a measure for how clique-like the neighborhood of a vertex is. Let's say for vertex I, I'm looking at how many triangles this vertex is incident to, and I divide it by the maximum of triangles this vertex can participate in. So if it's 1, your neighborhood is a perfect clique. So all your neighbors are also connected to each other. So that's the maximum value it can reach. And you can define it for the full graph, the global clustering coefficient. Then you look at the total number of triangles in your graph, and you divide it by the potential number of triangles. And that gives you the global clustering coefficient. What you see on this figure is, well, there's two pieces of two things that are important for me. One is the black points there. Well, first I should explain the figure. Well, for this one, we look at or compute the clustering coefficients for all the vertices, and for vertices of all vertices with a given degree, let's say degree 5, we look at the average clustering coefficient for all vertices of degree 5, and then we plot it. So black points correspond to the real data, actual data, and blue points correspond to Chung-Lu. Well, an instance generated, that's another graph with a similar degree distribution. And we also have the stochastic Kronecker graph and noisy stochastic Kronecker graph that we propose that fixes the fluctuations of SKG, fixes the fluctuations in the degree distribution of SKG. So there's a big gap. These models, there are some of the better models that are around. They cannot regenerate the clustering coefficients. And the second thing is, a little much more clear here in this case. The clustering coefficients decrease as you increase the degree. And they're extremely high for small degrees. For on the top two, well, they're the quarter-ship graphs. They're almost 1. So that means these clusters are all, they're clique-like structures, especially for low degree vertices. And gradually they decrease. And for other graphs, well, these graphs they don't have any, the clustering coefficients are not too high. Still, you see the same pattern. The clustering coefficients decrease as the degree increases. All right, so these were observations, and so what did we do? So what is our model building approach? What we want to do is, I want to find features in these graphs, and that will restrict the search space. And once I do that, if I can restrict the search space, then I can use results from external graph theory. So if I need X and Y and this and that, so what can the graph, what should the graph look like? And then in that limited search space, we can generate our graphs. So in this case, let's say, well, I want a skewed degree distribution. So this is something we can all agree on. Yes, these graphs have skewed degree distributions. The second one property feature is, I want high clustering coefficients. So let's think about it for a minute. So how we can design a graph with these features. And just as an exercise, let's take it to an extreme, and we want to make all the clustering coefficients to be 1. If my clustering coefficient is 1, what it means is, if you want to be friends with me, you should be friends with all of my other friends and nobody else, period. So I don't have any tolerance. My clustering coefficient is 1. And in graph theory, we call that a clique. And well, everybody is connected to everybody else. Well, and since the graph is still sparse, it's not a giant clique. It's a union of cliques. So really disconnected, the graph should be a bunch of disconnected cliques. The second implication is that, well, the size of the cliques should follow the same distribution as the degree distribution. Because if I'm on a clique, my degree is D, and if I'm on a clique, that means there are D plus 1 vertices in that clique. And if you give me the degree distribution, well, your communities or cliques, we should follow the same distribution. But of course, the challenge is in the gray area. The clustering coefficients are high, we know that, but not that high. They're not 1. So what happens in the gray area? So what we did is, all right, so let's start with, this is our approach. Let's start with the observations, or we can call them assumptions. They're fair assumptions. I want to graph with a degree distribution, skewed degree distribution, and high clustering coefficients. So in that case, we can prove that, well, if a community has S edges, and there must be, well, in the order of square root of S edges with degree square root of S. So essentially what this is, I'll not try to explain this theorem, it needs a lot of quantifiers. What essentially it says is, this clique assumption for the extreme case essentially holds in the gray area as well. You don't need, in this case, you don't need cliques, but you still need dense structures. And if their sizes follow the same pattern, they should follow the degree distribution pattern. And then based on that, we can build a hypothesis. So this is what we claim the graph should include. And the main point I want to make here is that, well, the real challenge in modeling is not coming up with a formal model. The real challenge is formalizing the model building itself. Because otherwise, if I know that, well, these graphs should have triangles, and I can just throw in a few triangles in that, that's not a big issue. And you can say that, well, I want also butterflies in my graph. I can just put butterflies and roses and rabbits and everything else you can think of. But the challenge is, how do I formalize this? So in this case, I'm starting with the measurables. In any graph, I can measure the degree distribution, and I can measure the clustering coefficients. And based on that, I can formally claim that you should have these dense structures in the graph. And some more exercise, of course. Well, this is our claim. And if the claim is true, well, there should be the number of communities in a graph should grow with the number of nodes. So that means that the largest community should be in the order of, the size of the community should be a constant. So it should not grow linearly. And actually, if you look at all the results in the literature, and some of them, the authors are here, actually, we know that the communities, they don't grow actually. They're very small. Like 200 is a critical number. You don't see, the size of the communities do not grow as the graphs get larger and larger. And the famous claim is here, the Dunbar number. And here's another prediction. Within a community, the degree deviation, the variance should be small. And what we can measure is, well, since we cannot find these communities, I'm staying away from that. But instead, what I can verify is that the vertex, the degree of a vertex is correlated to degrees of its neighbors. And if I look at all the triangles in these graphs, they're close in degrees. So we have experiments and we can verify these things. All right, so this is the concept. So that's the core idea about how we want to build our model. So we can now think more algorithmically. And I know there should be dense structures in my graph, but how do I generate these dense structures in the graph? Any method, my claim is that any method that assigns the probabilities of edges in advance and then just draws edges randomly cannot generate good triangles. And the reason is that, well, these graphs are extremely sparse. And what it means is just pick two random people. What is the probability that they know each other? It's essentially 0, because these are extremely sparse graphs. But if I say that these two random people I picked, well, they have a friend in common. What is the problem now? What is the probability that they know? The probability all of a sudden jumps up. So that's because of the clustering coefficient. So if you have a common friend, instead of 0, the probability becomes 0.4, for instance. That's extremely high. And to satisfy that, well, you need some history, because all of a sudden the probability of two people being connected depends on other things. So that's conditional probabilities. So you should even do this sequentially and generate a few edges, and then before adding a new edge, you should look at all the history, which slow things down. And especially a reminder that I want to remind that we're looking at generating extremely large graphs. So that's not possible. So the solution is you have to embed these cliques or these structures into the graph. And then you can say, well, I know that these people will know each other, they're more likely to know each other. And if you belong to that group, the probability of getting connected will be higher. And well, we call these things affinity blocks because we run out of words, and believe it or not, because all the other word terms we could think of, they have also pre-assigned meanings, and it's easy to get confused, so we call them affinity blocks. So we made a simplifying assumption that we'll have non-overlapping blocks. And the second thing that's in the choice of these blocks is, what do we put in these blocks? We know there should be blocks, but what should we put in these blocks? And our claim is that these vertices should be close in degree, and think about it. So everybody wants high clustering coefficients, and I'm the cool guy with 1,000 friends, and there's another person with degree 10. Do I want to be connected to that vertex? Well, I want clustering coefficient to be high, and if I have a degree 1,000 and the other vertex is degree 10, well, it already used one edge to connect to me. That means it can only at most connect to 9 of my other friends, which will decrease my low clustering coefficient. So I'd like to be friends with, connected to other vertices with degree 1,000 to keep my clustering coefficient high. So that's the idea. And what we did is, well, we took it to an extreme. And for convenience, we block all these vertices of the same degree into the blocks. So not exactly, they don't have to be of the same degree, but they're all close in degree. So we choose these affinity blocks form the affinity blocks of vertices of similar degree. So one important thing here is this way of forming communities, well, it's consistent with Dunbar's number, or consistent in the way how the size of the communities should scale. So the largest communities, if you think about, we can prove that if you have a clustering coefficient, if you have power law degree distribution and your power law coefficient is 2, the largest block should be in the order of hundreds for a graph with 1 million vertices, and it should grow very, very slowly. So, well, this is consistent with the way, well, with the other results in the literature. The other thing here is, important thing here is, well, we're not specifying each block one by one. The total information is in the order of number of distinct degrees, or the maximum degree, for instance. And that means, always says, well, we have in the order of, well, the number of communities in the order of the number of vertices, but information here is much smaller. So we have a low dimensional representation of the community structure as well. So this is better or better. So that was our lame attempt at humor to say, well, it's a better model, so let's call it better. And so 3 phases are first we group vertices together, and within each group, we form dense Erdos Renyi graph. So it's not a clique, it's still sparse, but it's relatively dense. And in the last phase, phase 2, we look at all the remaining degrees and make sure that the degree distribution is satisfied. And I've been talking about scalability, and actually the way we implement it in the new version is that we can compute the probability. If you give me the concomitant structure, I can compute the probability for each edge in the graph. And I can implement this in a streaming way and by repeatedly inserting edges to the graph. Or you can run this in a streaming graph generator, or you can do it in a parallel way. Each processor independently inserts edges to the graph. All right, so I would like to show this one because when I explained this, give this talk before, people that envision a matrix where I have giant blocks on the diagonal, and a few non-zeros as well, like more scientific computing or block-angular, block-diagonal matrices. That's not it. Well, what I'm adding in phase 1 is the edges for affinity blocks correspond to the red points there. So it's a very small portion of the graph, and these blocks are extremely small, and they should be extremely small. And well, if you amplify it, you see the repeated structure. So they're right on diagonal, but they form a very small part of the graph. Most of the graph is formed in phase 2. And just for fun, well, we generated large graphs and visualized them for here's we have the color of the orthovertices indicate its degree. The darker means denser. And blue lines correspond to the edges of the first phase, and the green lines correspond to the edges of the second phase. And well, it was just for fun, and it was it's a good visualization of the model. All right, so can we regenerate the graph properties? So here what you see is, well, we took one graph, this co-authorship graph for astrophysics, and we have the BTER and CL versions, and we compare them. And degree distribution, the first plot is on the left is the degree distribution. Yep, we can reproduce the degree distribution. CL can do the same thing, so that's a check. That was not too hard anyway. The one in the middle is for clustering coefficients. And BTER, well, matches them almost perfectly. So the clustering coefficient distribution is very extremely close to what you would what you expect. Well, we use it as a guide anyway. So forming these triangles are motivation for BTER anyway. So we were able to reproduce that. So that's another check. The interesting part was, well, we looked at the eigenvalues of this is eigenvalues of the adjacency matrix. And well, the match was surprisingly good. And first thing, one thing I want to say here is, well, eigenvalues, there's some myth that the eigenvalues are distributed by the degree distribution. So there are actually solid results about this. If you're talking about the random graph with a given degree distribution based on the Chang-Lu model, yes, the eigenvalues will be determined by the degree distribution. But in this case, this is not a random graph that's determined by the degree distribution, and you cannot use the degree distribution to predict the eigenvalues. And they're way off for Chang-Lu, even though degree distribution matches almost perfectly, but BTER matches these eigenvalues very closely. And the overall clustering coefficient and the size of the largest connected component, they're close as well. So this one I wanted to show because it's a trust network, and the clustering coefficient is relatively low. It's 0.07. So it's not an extremely high, it's not a graph with extremely high clustering coefficient. But we're still doing a reasonable job. The degree distribution, again, is not an issue. Well, everybody does well for that. And clustering coefficients, BTER is, again, very close. And again, well, eigenvalues are close. So that's eigenvalues over there, that's a global property. And if you're matching the eigenvalues You should be doing something right. Of course, when I first looked at these results, I was just looking at it. Well, eigenvalues are just off by 10%. We nailed it. I'm perfect. But now I'm looking at the same results. Well, we're off by 10%. So what is going on? So we're missing something. And yeah, that's something. Of course, there's always no end. There's no stopping. We should now think how to improve these results. And the major point here is that BTER provides still good approximations, even though the clustering coefficients are not that high. All right. So to conclude, the first thing I want to say is that, well, models are important. And models, it's a very difficult problem. It's a very intriguing problem. And I think it should be the way, it will pave the way for many discoveries. So, and I would encourage you to think about how to build these models. And I'll repeat my claim that, well, statement that the main challenge is not coming up with a model, because you can improve your models in an ad hoc way. Just always, well, tell me what is missing, and I'll just add an if-then else statement in my model and generate a few of these things. So you can always improve your models in an ad hoc way. But the challenge is formalizing the model building process itself. What do I measure in these graphs? What do I measure that can be measured consistently by different people on the same graph in the same way? So what are these metrics? And what do these metrics imply for the graph structure? So we should do it in a more principled way. And this makes the problem extremely hard. And for this talk, we were able to, well, I already described the model to you. And there's some theorems that underlie this model. So it says we can prove that you should have, if you have the skewed degree distributions and high clustering coefficients, you should have dense blocks, Erdos Renyi like dense blocks in your metrics. And that's independent of how you implement our model. So based on this observation, we implement a model to realize these dense blocks. And we were able to generate graphs that are like the real ones. Well, the codes are available at, well, you have the URL, and this is everything. Well, if you look at our paper, and if you look at this, you can regenerate everything we generated in the paper. And before taking the questions, so another small announcement. So some of us are working for a workshop on network science. So if you're interested in networks, so we are planning to have the first workshop co-located with the next annual meeting, and it will be in San Diego. And if you're interested, please let me know. And I'm hoping that we will increase our presence. The workshop will increase our presence within SciEm. And with that, I'll stop and take your questions. Thank you.
Thank you. Can you repeat the question?
There are many properties of the graph. So there's degree distribution, and clustering coefficient is only one of them, or two of them. And there will be many other metrics of interest. So why don't we look at them and see that if we can mesh them as well. So we looked at some of the other techniques like average degree distribution. Well, they can be matched closely as well. And we believe these things are more critical, they're more descriptive, and we mesh them. If there is something we cannot match, that would be great to see, because that means it will point to either a shortcoming of the model, and we'll later see why we're not matching it and improve the model. So if you can't think, well, of course, there are some of the specific applications. There are very specific things they want to preserve. So if you have any specific suggestions, I'll be very happy to hear them. And and of course, this is a model. It's an imperfect model. That needs to be improved. If there is a property that we cannot match, we'll go back and figure out why we cannot match it, and then improve the model. So that's the model building process itself.
Okay, thank you again.
Well, thank you.
And it's time for a coffee break.